Hi, I'm following along with Paul McWhorter's Raspberry Pi Pico lessons, and I've already submitted the quick and dirty homework for uh, lesson 25 of drawing circles on an OLED, and several other people have beat me to it by a few hours. Every three of us posted um, uh, this solution just today, so um, we all spent the weekend figuring it out, I guess, or whatever. Um, Anyhow, the I'm sure that Paul probably was thinking that we were supposed to do it with math rather than using the inbuilt function. The quick and dirty way is to use the ellipse function that recently became available in the frame buffer class that they have built into the uh, MicroPython. So anyhow, so I had spent all week before that. This was like an afterthought to go look and see, well, is there really an inbuilt? Because, a lot of people just said, oh, there's no inbuilt. And I went, all three of us went and looked at it and found it just recently that, that there was that ellipse function. Anyhow, but I had spent many hours deep diving into how to plot circles around the X and Y of a raster OLED screen. You got X and Y on there. And it's amazing how many different ways there are. There was six or seven people, or six or more people have already posted their homework videos, and almost everybody's doing it a different way. A couple people did it a little different, but or did it close to the same, but most people are doing it um, uh, different ways. So that was very interesting. So I had already been thinking about it, and I had came up with several, and I thought, well, okay, what else can we do? So I started searching. But as people started posting their videos, there was one person, I guess the normal way, and probably the way Paul would want to do it, is you just use cosine and sine to plot all your points around the circle. Um, but he that's probably the way. And so you're going to go 360 sine and cosine calculations. And you're also going to, plot those points. But one person posted code that he said that he kind of found on the internet and modified. And it used only 0 to 90, and it actually used the way you use the symmetry of the circle to be able to get the other ones with just pluses and minuses. So, and show you what that is and why that might be important. So here's a circle, and like I said, we don't actually plot a nice even circle around there. No, this is way blown up, but even on if you do, this is a 10 pixel radius circle, that's where your pixels are going to be. When it's nice and small, it's going to look more like a circle than this does. But anyhow, like I said, Paul's thing is that you're going to, or not Paul's, but the one person that posted a video said that, okay, you're going to do 360 um, calculations around here. And I think some people either figured that you don't need that many, or maybe you didn't, um, unless you had a big circle. But anyhow, you can see that this 10 pixel radius circle, there's only 14 pixels on a quarter, so there's only 56 around the whole circle. So you don't really need when you do your sine and cosine, you're going to get a lot of duplicates in there if you do 360. So a lot of them just did like step 2, you take in every other degree, and that gives you 180. That's still enough. But if you wanted to make a little bit bigger circle, that would be okay. And I actually did the calculations that if you did uh, 180 calculations, that your circle would have to be bigger than 32 pixel radius before you'd start missing points. So you either have one on here where it's either next to each other or catty corner, you know, diagonal from it. So there's always one. But if you made a big circle, of course our small screens aren't going to do that big a circle. If you did that, then you might end up with a space here. You might have one here and one over here or something like that, with not counting this one. And so doing the calculations, it's once you get above 32 pixel radius, then you get over 180 dots that you're plotting. So if you're only doing step 2, then you wouldn't be able to do it. And of course, that's a linear function. So once you get over 64, then your 360 is not also, once you get over 64 radius, then you're not going to have that pixels. You're going to have, more than 360 dots. So at that point, you got to either take fractional degrees or half degrees or whatever. But like I say, our displays aren't, radius of 64 is going to make it, off the screen no matter what. So unless you had a bigger OLED. So anyhow, so that works. But the thing is when you're doing it, like I said, we only, even on this 10 one, you only got 56 pixels. So you're doing either 180 or 360 calculations. So you're actually wasting the processor's time doing that. And then, like I said, well, one guy said, you really don't even need to waste your processor's time doing that, because you have symmetry in your circle. So if you plot one point, you can plot 4 more just by doing the math, plus and minus and everything. So if you plot this point here, that's actually whatever, let's just say that this is, we can't do 0, 0, but let's just say that this is 0, 0. So you got to remember that these are actually coming from the top. So if you take your X and, your Y, and you add this to it, then you're going to be at this pixel. So if this is 0 and you add 7 to it, you're going to be down, or 6 to it, you're going to be down here. 1, 2, 3, 4, 5, 6 to it, you're going to be down here. But if you take that same thing and you say, and that's Y plus 7 and X plus 6 is what this pixel ends up being. But if you take your, subtract a 1 from it, your Y from it, instead of adding Y from it, then you're going to end up with this pixel. Same way with the X. This is the plus side of X, but if you did a negative X, you could do that. And if you do a negative X and a negative or a Y, then you would be here. So anyhow, so you can do symmetry there. So that way you only actually need to calculate these points, and then you can just, with cosine and sine, which takes up more processing power, and then you can just use simple addition and subtraction to plot the other points on the other 4 quadrants. Well, you can also take that one step farther, because you have more symmetry. If you take and draw 45-degree diagonals in here, you also are able to symmetry here and here, as well as here and here and here and here. And I'll show you it's just a matter of plus and minuses and whether you're using X and Y, and you get that. I had to sit there and actually plot out some, because I didn't believe that was working, but I'll show you that in my code that works. And so we'll get to that, and then I'll leave, going to make this small, but we're going to come back to this. So let's go ahead and get to the code, because that's what I started with, and I'm not even sure where I am. Yeah, OLED. So this is a basic program, and I got a lot of different functions in here for ways of drawing that. So here's just a trig circle where all you're doing is going from 0 to 360 and you're stepping by 2, so you're doing 180 calculations, and you are doing the sine and cosine and getting your x and y, and then you're just plotting those pixels, and then I'll show you down in the main function. We do a show after we run this. So this plots all the pixels to the frame buffer, and then we just show it at the end. So here's the one that just does the math on all 360. Now this is the one that a fellow, he only had 4, but this is going all the way to the 1/8 circle. I didn't want to bother going to doing them all. I got enough as it is. So this is the 1/8 circle. So that way all you got to do is 0 to 45 and you're stepping by 2. And you're doing the same thing here. So, but here's the thing, is that you can get your, by doing x plus 0, these are the ones that are in the 4 point, these first 4. So you're minus x and plus y, and then you got plus x and minus y, and then you got minus and minus, and then you got plus and plus. So you got, all 4 combinations there will get that. And here's where I had to actually go back to that grid and figure it out, because you also have 4 more. So you got your x0, your center that you're doing, and then you can do the same thing by swapping out the y's. So you got y, and this, because this tilts your symmetry by 45 degrees by using the opposite, and you got you're acting on the center x by the y coordinate, and you're acting on the center y by the x coordinate, and you're doing the same thing, a plus plus minus plus plus plus, and then anyhow you're getting down here and getting all those. And I'm on, the code's there if you want to go try it out, and then, but it just shows that it works. So anyhow, so we'll go back, and so we're at 1/8 of the circle. So I'm going to go back to our thing. So if we're only using 1/8 of the circle, and I actually thought of this on my own, but I confirmed it by others on the internet, is that not only do you have cosine and sine to do this, but you can also use your square root function to find out these, because we know our well, not just square root, but your old Pythagorean theorem for right triangles. You know your radius for each of these, and you're also, if you step through the x's, you're going to, or step through, let's say we step through the y's, because we'll start down here, and we'll step through the y's, and you can do this. Remember that we had, there's 50 in this circle, there's 56 points, and we were doing 180 calculation, or 180 calculations, and so we actually 1/8 of that is 90, 45, 22, 23 calculations or whatever. But we actually only have 1, 2, 3, 4, 5, 6, 7, 8 points in here. So we're still doing, even with the 1/8 of circle, we're still doing a lot more calculations than we need to with the cosine and sine. Of course, you got to do a cosine and a sine for each of these points. So if we do use Pythagorean theorem on this, you know your radius. So a squared plus b squared equals c squared. So if this is our x. So we know our x. So that is our radius here. So if we step through our radiuses and come back, or is it our y? Maybe, I don't know. But anyhow, you're using Pythagoras and you're doing each one of these. So you're stepping through this and you're seeing, okay, so if I move up 1 pixel, is what is the and we know that the X is still out, or we stepped up in Y, so that now is the X going to change? And as you can see, it didn't change. So if we step up another in Y, is the X going to change? And if we step up another, is the X going to change? But then if we do the next one up, we go up to this row with our with our Y, is the X going to change? And yes, it does, in the same way. So we can do that. So 1, 2, 3, 4, 5, 6, 7, 8 calculations, and we can use square root and find it that way. So let's go down to our square root, and we have our square root of the eighth of the circle. So the thing about this is you, because you don't want zeros in your square roots and stuff like that, you put your base circle, so you're taking your radius and you're subtracting the X and you're adding the X, and then you're doing the same thing for the Y. So anyhow, you got that. So my timer's running out. It looks like Zoom is actually enforcing their time limits now. So I got 9 minutes left to finish this. Okay, so now we got the first pixels, our polar, our coordinates, X and Y, plus and minus coordinates, because we know them. We don't have to. They're just regular plus and minus. So that actually takes us down to 7 different things we got to do. So now all you got to do is so if you're going up, all you're worried about is if X is staying smaller than Y. Once X becomes equal to or greater than Y, then that means you're past 45, so you don't need to do those. So that's how all we have to do is do that to make sure we don't do too many. So then you're just doing, like I said, you're taking your square root of R squared plus your X squared. So we're starting with the X value of 1, because we already figured X0 up here. So this is X1, and then you're working through that, and then you're setting those pixels the same way we did up there, the 8 pixels, based on whatever the Y is. So you're incrementing X, and then you're figuring out what the Y is, and with the square root. And then, like I said, every time you increment, and then you do that until X is larger than Y, and you get that. So anyhow, that was the next one. So that was a little bit of the ones that we knew that were using the math function. And I also knew that Adafruit has what they call the graphics library. So I said they had it. I knew I used it in Arduino, and they had ported it over to their Circuit Python as well. So it's a little bit different, but it was easy enough to convert it back to MicroPython. So they have a library, and the thing about that was, and I had to really look into why they do that, but let's show you the library, or the function first. So as you can see with the Adafruit, they don't have anything in here except for plus and minus comparisons, and I think this is the only place they use a multiply. So they only use multiply in much of it. But they have this thing, they call it this variable called DDF, and I didn't know what that was. So I said, oh man, what is that about? And if you can see, this is all they're doing, and they're coming up with an X, and they're changing this DDF to see if it's a certain value. And I said, oh, what are they doing here? And then they set them again, and that's the end of it. But this basically is all the code that they're doing to find those. Again, it's just 45 degrees, and then you're setting the other ones. And I had to go deep diving. So let's get out of that. And rush over here and see if I can find something up here that I'm looking for. So I found this, and this is where I actually stole these things, and they were using the square root. So I found this one on midpoint. Come on, there we go. So they were talking about this midpoint algorithm, and look at all this math. Look at that math. I tried to work my way through that math, and I couldn't figure out what they were doing. So anyhow, they that's the math, and then when they boil it down into it, they come up with code that is similar to what Adafruit did, and they call it the midpoint. But it's a little different than Adafruit because they're doing sort of like a 2 times y and 2 times x, and I don't know what that's about because Adafruit didn't use that. So this is called the midpoint one. So I assume that it's some form of that. And well, I got one more up here, I think. I might not. Oh, here it is. So here's another one. This paper, let's go down to the bottom real quick. This paper is from February of 1977. So, and it's from some Lutheran college. So anyhow, this is another one. This is on the, how do you say it, Bressenham circles. And I'm honest, I'm not going to say that I knew all this math, but this is like the first thing. And this is like linear algorithm for incremental digital displays. So we had that DDF on there. So I imagine digital display calculation. So I'm thinking they don't actually give you a code for this. This is, I think, Python for sure. And who knows what code it was actually written in, but they give you like diagrams of how you would solve it and everything. But I'm thinking that Adafruit is using a form of this Bressenham circles algorithm. So that's enough of that. Let's get back. I'm going to run out of time here. So anyhow, so I'm using the Adafruit one here, and it's just using this Bressenham or whatever it's doing, and it's finding it out. So you don't even have to have the math imported to do that. So you saving from having to load your memory up with the math cosine and sine functions, or even the you don't even need square root function there. And then this is the midpoint circle, and it's like I say, it's similar, but I imported the code and it's about that same thing, but it's doing the same thing. So anyhow, let's get down to what I wanted to do with this. I found all these things. I wanted to say, well, which one's fastest? You can probably see I haven't updated this, so it's already there. You can probably guess which one's fastest. But you got to remember that we're actually plotting this with the OLED, and we found that in my last video, I showed that almost 25 milliseconds is used just moving the frame buffer from the Pico to the OLED. So you can probably take 25 milliseconds off of this number. So that'd be, instead of 26, it'd only be 1 point something to do this. So, and then I also did the built-in OLED timing is this one with the ellipse timing. So just to show it's running, I've got my phone here that I got, and I didn't even show it. So it's actually doing it. And it's actually, I don't even think you can see it, but it's going to run. And it actually did all the circles just that fast. So it did 3, 4, 5, 6 circles in that amount of time, blink of an eye. But you can see that by doing this, your trig turned out to be the most expensive. So if you take, let's just say we're going to take 25 milliseconds off of this. So this is basically taking 30 milliseconds. And this one, by taking the 45, trig of 45 and doing the plus and minus on the other ones, you come down to just 9 milliseconds. But when you use the square root on that, you're actually just taking a little over 2 milliseconds to do that calculations. And as you can see, the midpoint 45 and the Adafruit, the midpoint and the Bessemer is 1, and then the built-in ellipse, because it's probably using some C code behind the Python. The MicroPython is how a lot of them inbuilt things are working on the C code. It's doing it just a little bit faster. So if you take 25 off there, it's still taking about 1.5 milliseconds to do that. So to do the calculation. So you're going all the way from doing the trig at 30 milliseconds to 9 to 2 to 2 to 2 to 1.5. So, you know, the calculations in the grand scheme of things, you're not really doing that unless you wanted to draw circles really, really fast on there. You really wouldn't care.